So today's lesson, we're going to use something called the quadratic formula in order to help us find zeros and find solutions to polynomials. These can be either real or complex and imaginary. And at the end of the lesson, you'll kind of see that closing comment when we had pairs of polynomials and the imaginary part was flipped. You'll kind of see where that comes from. So we're going to start it off with some explore problems to just kind of set this up. We're asked to solve for x in problem 1 here. So we have x squared minus 7x plus 12. If you remember, we want to get this stuff into factored form in order to solve. So we want to get something that looks like that and have that still equal to 0. This is one that we could probably factor just by inspection. We can also use our little puzzle, multiplying to 12, adding up to -7. In this case, we'll need -4 and -3 to do that. So our factored form is x minus 4 times x minus 3. And the zeros there, or the solutions there, would be x equals 4 and x equals 3. Pretty straightforward, right? We've done this before. However, if we go over to problem number 2, you'll notice that now we have this 2 in front of our x squared. Our x puzzle over here, the sum and product puzzle, only works when we have just an x squared out in front and then 2 other numbers on our second and third terms. So with this one, we cannot factor with our puzzle. So we're going to need something else, and this something else that we're going to need helps us factor literally any problem we have that goes to the second power. It's called the quadratic formula. So if you scroll down here, you see when solving quadratic equations with the form ax squared plus bx plus c equals 0. Okay, notice how this form kind of matches what we had in our Explorer 2. 2 is our a, 2 is our b, -12 is our c. We can solve for that x by using this formula here. So let's see how it works. We're literally going to take that Explorer problem 2 that we couldn't factor. We're going to go ahead and factor it now by using the quadratic formula and solving for those zeros. So first thing I always like to do is identify what are my A, what are my B, and what are my C. I'm going to color code this first one. A is equal to 2 in this first problem. B is equal to 2 as well. And our C here is -12. So just a quick labeling so that we can use this formula. Once we have those labeled, we can plug in exactly what we see in our quadratic formula to come up with x. So in this case, x equals, we'll have a big fraction here. It would be -b, so in this case, -2. Let me color code that first step. Then we have this weird plus or minus sign. We'll see what happens with that later. Big square root sign. And we get b squared, so 2 squared minus 4 times a, which is blue, times 2. And purple was our c, so times -12. We go ahead and extend those lines out. And that's all over going to be 2 times our a variable, which again was 2. Right, so you'll notice that all we did was just plug in our a, b, and c values into this quadratic formula right there. So now that that's set up, we just got to evaluate it. We set x equal to it, and we have all numbers over to the right. So we can just start evaluating that step by step. We get x equals, we'll get our whole big fraction here, and we know that on the bottom 2 times 2 is 4, so let's just write that in. And we have -2 plus or minus the square root. 2 squared is 4, and minus 4 times 2 times -12. So that'll be plus 96. And we can rewrite that and just start trying to simplify underneath that square root. We get x equals big fraction here, negative 2 plus or minus the square root of 100 all over 4. Okay, square root of 100 should be 10. So now we get, now we get equals to negative 2 plus or minus 10 divided by 4. And here is where our weird plus or minus sign comes into play, and I'll make this sign in red here. Plus or minus. What it's telling us is that we're going to do it one way with the plus, one way with the minus. And if you go back to our original problem, we should have two solutions, right? Because we have a second degree polynomial. So we go back down here. We're going to work it two different ways. We're going to work it as x equals negative 2 plus 10 divided by 4, and x equals negative 2 minus 10 divided by 4. If you work that out, on the left here, we get x equals negative 2 plus 10 is 8. So 8 divided by 4 is just 2. And our second solution, x is equal to negative 2 minus 10, so that's negative 12 divided by 4 gives us negative 3. All right, let's continue practicing this. In example 2, I would recommend trying this by yourself to start, but maybe let's first identify A, B, and C. A in this case, since there's nothing in front of our x squared, A is going to be equal to 1. We can assume there's a 1 there. Our B is equal to 2. Our B is equal to negative 7. My apologies. And our C is equal to positive 12. Okay. Now, if we keep going, we want to set up our formula with this stuff that we just wrote down. I'm going to switch over to black here. We get x equals negative b is a negative 7, so it's going to be a positive 7 there, plus or minus the square root of b squared is negative 7 squared minus 4 times a is 1 times c is 12 all over 2 times 1. So just taking a, b, and c, plugging it into our quadratic formula. Then we just start evaluating. So x equals, we'll get 7 plus or minus. The square root will be 49 minus 48 all over 2. And we get x equals 7 plus or minus the square root of 1 all over 2, which is just, the square root of 1 is just 1, right? So we get 7 plus or minus 1 all over 2. Here's where we can then use our plus or minus sign to kind of split our problem into two separate ones, right? Because we're finding two solutions, so I'll write a little and in between here. We get x equals 7 plus 1 divided by 2, which in that case, x is equal to 4. And we get x equals 7 minus 1 divided by 2, in which case x is equal to 3. Now, we are going to boost that complexity, okay? Don't stress if we're not mastering it yet. It's not going to be required on our district test or end of course test, but it is a good thing to get exposure to and refresh because you probably hit it in Math 1 earlier. We're now going to see in example 3 and 4 some examples where we get imaginary roots. But we're going to start by solving these problems exactly the same way. All right, so identifying A, B, and C to start. Our A variable is going to be negative 1 in this case. B is 4, and C is negative 5. With that, we can set up our quadratic formula and make sure you guys are actively engaged in this, pausing, unpausing, trying it out on your own. We get x is equal to negative b plus or minus the square root of b squared minus 4 times a, which is negative 1, and times c, which is negative 5, all over 2 times a, which is negative 1. All right, then we start evaluating it. Let me scroll down a bit so you have some space. Get x equals negative 4 plus or minus the square root. And here we get 16. And we have 3 negatives multiplied in a row, so this will actually be minus 20 all over negative 2. That will give us x is equal to the minus 4 plus or minus the square root of negative 4 all over negative 2. And here is where those imaginary numbers come in, right? Because we are taking the square root of a negative number. So we want to use that imaginary number to handle that. If we rewrite that again, that will become negative 4 just stays the same. We have our plus or minus sign. That negative 2 stays there as well. But now we take the square root of the positive, so that'll be 2i. We can then simplify that further just to get a real and imaginary number here. If we use we're going to do our plus minus now to solve both of these. We have x equals negative 4 plus 2i divided by negative 2, and x equals negative 4 minus 2i, all divided by negative 2. And you can start to see now when we talked about the pairs of imaginary zeros before, where that plus and that minus, that flip in our imaginary zeros comes into play. And if you simplify these out, we haven't worked with fractions yet this year, but if you recall, we can split that denominator so it impacts both of the terms in our numerator. We get x equals negative 4 divided by negative 2 plus 2i divided by negative 2. And we can split that other one as well, negative 4 divided by negative 2 plus a minus 2i over negative 2. And we can simplify it out to close out the problem. X equals negative 4 divided by negative 2 is positive 2. And we have a mismatch on the right, so it'll just be 2 minus I. So the 2's cancel out. And again, x equals 2. This will simplify out to plus I. And those are your two solutions there. Again, notice that mismatch between the pairs of imaginary zeros where we flip that imaginary number. All right, let's do one more problem. Again, practicing with imaginary. Start off by identifier A, B, and C. So A is 2, B is negative 12, and C is 26. Starting to deal with slightly bigger numbers here. We rewrite our quadratic formula, x equals negative b. So in this case, we're taking a negative of a negative. It's a positive 12, plus or minus the square root of b squared. So that negative 12 squared minus 4 times 2 times 26, all over 2 times 2. And we just start simplifying once that formula is set up. So 12 plus or minus the square root, 12 squared is 144. And we are subtracting 208 from that. And that's all over 4. Slide down so we can see a little bit better. So if we simplify that further, we get x equals 12 plus or minus the square root of negative 64. Again, we're taking a square root of a negative, so we'll want to make sure that we are using our imaginary numbers here. Taking that square root of the negative 64, so that will become 12 plus or minus 8i all over that positive 4. We can use our plus and minus to split. So we get x equals 12 plus 8i over 4 and x equals 12 minus 8i all over 4. We can start simplifying it out by breaking apart that fraction. We get x equals 12 divided by 4 plus 8i divided by 4, and x equals 12 divided by 4 minus 8i divided by 4. So our answers here will be x equals 3 plus 2i, and x equals, where we flip our imaginary number, 3 minus 2i.